If everybody's present, now we can start. This is a PhD defense. It's not a proposal. Yesterday was a proposal. Today is a defense. That means that it's the last phase of Stephen's work at University of Delaware. Stephen is presenting today, but officially is graduating at the end of summer, which means that any work that the committee will ask him to do have to be done for July.
Yeah, it's mid-July.
Mid-July, 18th, exactly. As usual, there is a procedure. We start with a presentation of 45 minutes approximately, in which Stephen will defend his work, and followed by the question of the committee. We give priority to the committee to ask questions, and after that, the public, which is quite large, our committee remotely cannot see that, but it's a very impressive participation. Thank you, everybody. You will have opportunity to ask your questions, at the end of which we ask everybody to leave, also Stephen, and the committee will discuss the case and take a decision. So, Stephen,
great.
Good luck.
Thank you all for coming out for this. Today I'll be talking about advanced schedulers for next generation HPC systems. And I'd like to start by thanking my research advisor, Dr. Michaela Taufer, and the other members on my committee, Dr. Sunita Chandrasekaran, Dr. Rui Zhang, Dr. Dean Hildebrand, Dr. Martin Schultz, and Dong An. I'd also like to thank all the collaborators at other institutions like Lawrence Livermore National Lab who made this research possible. And I'd especially like to thank the Global Computing Lab members here, many of which are in attendance, that made the past 4 years exciting and provided a great environment for research and collaboration, and provided spare laptops when my laptop would not boot. All right, so before we can talk about next generation schedulers, first we want to understand some trends that are happening in next generation systems. So one of these trends is a widening I/O gap. So you can see here 3 generations of systems cited at Oak Ridge National Lab. And over the course of these 3 generations, the floating point operations per second capabilities of the systems increased 64-fold over the 2009 system Jaguar. But the parallel file system I/O bandwidth only increased 13-fold. So what we have now is 64 times the flops available for science, but only 13 times the bandwidth to save that science out to disk. So there's a gap there that's going to cause us problems, which I'll go into later on. The second trend we're seeing is a rising importance of ensembles. So ensembles are workloads that involve lots and lots of jobs. One example is uncertainty quantification, where you submit millions of the same job and you tweak the input parameters to see how that affects the output. So the scientists at Lawrence Livermore National Lab, over the course of 3 generations of systems, have used these flops not necessarily just to run larger simulations, but to run more simulations. And we're seeing that trend extend into exascale. So how does this widening I/O gap cause problems for our system and performance? So the first way we see this manifested is in system performance. We just take a naive look at a recent simulation we ran. You'll see that we have the number of nodes being allocated by the scheduler over time, increasing up until the max limit, the maximum number of nodes on the system, staying steady, and then once jobs stop flowing into the simulation, the system drains and the simulation ends. So just naively, this looks great, right? Utilization's at 100%. We're using this big machine that we purchased. But if we take a deeper dive into what's actually happening on the system, what the cycles are being devoted to, we see that only like 70% of the time is spent in computation. That other 30% of the time is spent writing out to disk and blocking on I/O. So that widening I/O gap is coming to bite us here. And we see this also reflected in individual job performance. So as we shrink the size of the parallel file system relative to the amount of compute, we see that the variability of performance experienced by applications increases. And so you can run the same application many times, and sometimes you'll get 100%, sometimes you'll get 60% of peak performance. It all just depends on what other jobs are running on the system at the same time as yours. So to maximize performance, both at the system level and at the individual job level, our next generation schedulers have to be I/O aware. They have to consider this widening I/O gap. And then what do we do about these ensembles? How do these impact our system? So the first way is with scheduler overhead. So we did a test with Slurm, which is a state-of-the-practice scheduler at Lawrence Livermore National Lab. And we ran several ensembles, varying from 1 job to 130,000 jobs. And the applications within this ensemble have no runtime, so it's just sleep 0. So everything that you're seeing plotted here in terms of time is just scheduler overhead. It's just the time for the system to ingest these jobs, process them, and then record that they've completed. You can see that that overhead increases linearly with the number of jobs in the ensemble. We also see this reflected in submission failures. So in the same test, while we were recording overhead, we were recording the number of failed submissions. You can see that that also increases linearly with the size of the ensembles. And this is due to schedulers' queues filling up, them running out of resources like sockets or file descriptors, and generally create problems when you're trying to submit these ensembles. So to effectively manage these large ensembles, our next generation schedulers need to consider different and new scheduling models. So in this thesis, we claim to maximize the efficiency of next generation systems. Batch job schedulers must support I/O. They have to drive that I/O awareness with external I/O knowledge, and they must leverage fully hierarchical models. And to validate this, we integrate I/O awareness into popular scheduling policies to prevent I/O contention, and then evaluate the impact of that I/O awareness on system efficiency and scheduling costs. And we do this evaluation both with perfect I/O knowledge and with I/O knowledge provided by predictive tools. And then we design a fully hierarchical scheduler to improve scheduler scalability, and then evaluate the scheduler's job throughput and overhead on both synthetic and real-world ensemble workloads. So before I dive into any individual contribution, first let me talk about the current state of batch job scheduling so we are on the same wavelength. So in HPC, typically you have a group of users, each of which has their own codes or applications or simulations they want to run. And in order to run these, they have to write a job script. And what this job script looks like is you have some metadata up at the top, which is information or metadata you're providing to the scheduler, such as how long the application needs to run for and how many nodes it needs to run. And that's followed by code to actually execute the application. So these job scripts are submitted to the batch job scheduler, which is then it's then the job of the scheduler to map those scripts and applications to the compute resources. And it needs to do this fairly so no users dominate the system, but also efficiently so there's not incurred overhead. The main problem is there's a whole set of resources, in this case parallel file systems and burst buffers, that aren't considered and aren't under the control of the batch job scheduler. But we want to fix this. So to fix this, we need a foundation on which to build and a scheduler on which to integrate this I/O awareness into. So we target Flux, which is the next generation scheduler. It has three key features that help us here. It has designed for modularity, expressivity, and decentralization. So this modularity makes it easy for us to integrate new features and components. The expressivity allows us to describe the I/O resources that we want to target and integrate that into our scheduler. And then that decentralization is going to help us with those large ensembles. Okay, so now that we're on the same wavelength as far as scheduling, I can talk a little bit about how we integrate I/O awareness into our scheduler. Okay, so on a traditional system, applications are running on these compute nodes, and they're attached through a network to a parallel file system. And when the application wants to write out to disk, it writes directly to the parallel file system. And HPC applications typically are bursty. They go through phases of computation followed by phases of I/O. And when you have many applications running on the system at the same time, these applications can collide in terms of their I/O bursts. And so you see here a collision occurring. And whenever these bursts happen, that's when the contention occurs and our applications slow down. So system designers have to provision and procure these parallel file systems with these bursts in mind to try and handle them as efficiently as possible. So to handle the widening I/O gap and kind of improve this situation, what system designers are doing now is they're starting to purchase SSDs and putting them what are called burst buffers. And so what happens now, the applications write directly to the burst buffer, and the SSD can provide way more bandwidth than a spinning drive. So the application is able to burst, finish very quickly, gets more bandwidth, and the probability of any two applications colliding is reduced. But the data can't stay in that burst buffer forever. Eventually, it has to make its way to the parallel file system. And so it drains out asynchronously to the writing of the burst buffer. So you can think of this like a funnel, right? So I have a big wide mouth and a tiny hole at the bottom, and I can dump a gallon of water in the top, and it trickles out the bottom. But the problem comes in if I just keep dumping in water faster than it's draining out, eventually that funnel is going to overflow. So in order to examine this potential bottleneck further in between the burst buffer and the parallel file system, we needed an environment where we can isolate this and study it. So you'd think, okay, well, let's get a system and let's go run on this, right? There's 3 problems with this. First, this is going to require exclusive access to not only a parallel file system, but all the clusters attached to it. So that's a significant portion of the clusters at any HPC center. And then this is going to take a considerable amount of time to run. So if we want to run a week's worth of jobs, this experiment will take an entire week, and that's going to take down that portion of the center for the whole week. And finally, these experiments are going to be unique and hard to replicate. So it's going to make it hard to generalize any conclusions we come to. But if we turn to a simulated environment, now we have a controlled environment where we can test these things deterministically and many times and draw general conclusions, assuming that we pay attention to the modeling of system resources, the workloads that run on the simulated system, and the contention that occurs on saturated system resources. So there should be an animation here, but with the PDF. How do we go from our target scheduler Flux to a Flux simulator? Well, we wrote a deterministic discrete event simulator, shown here, which allows us to repeat these experiments in a controlled environment. And we base this off of an I/O contention model in previous work. And this I/O contention model is very conservative. So if you have a resource that has contention occurring on it, this model assumes that it's still going to operate at 100% peak efficiency. But in the real world, you would expect that the more people are piling on work onto a resource, the worse it's going to perform overall. So it's a very conservative contention model and kind of biases evaluations against our technique. A conservative assumption there, and then we use a workload model based on previous work as well. So using this, we can now test out our hypothesis of, does there actually exist a bottleneck? So to do this, we simulate a system called CTS1, which is a system that was procured at Lawrence Livermore National Lab. It consists of 3,800 nodes, and based off of the proposal where they procured this, this system requires a 70 gigabyte per second parallel file system to be perfectly balanced between compute and I/O. And the job traces we used are extrapolated from 2 smaller systems at Lawrence Livermore National Lab. So we didn't have access to the workloads running on this system, so we took 2 other systems at Livermore and extrapolated up. And these jobs use 18 megabytes per second per node. And this is based off of that same request for proposals when they procured the system, where they stated they wanted to be able to checkpoint half of the system's memory every hour. So if we run this experiment, we can see that with the perfectly provisioned file system, 70 gigabytes per second, that all of the time is spent in computation. So everything's great here. But if we reduce the parallel file system by 10%, all of a sudden now applications have to spend time blocking on I/O. And this trend continues every time we reduce the parallel file system bandwidth, until we see that 30% reduction now at almost 30% of the time is spent blocking on I/O. So indeed, to manage this bottleneck, we need our schedulers to be I/O aware. So how do we go about integrating I/O awareness? We start with the resource description language that exists in Flux, and we express the I/O resources that exist on the cluster, describe them. So for example, gateway nodes, network switches, the parallel file system itself, and we describe the limits of each of those resources. And then we expose those resources to the scheduler so that it can now take those resources into account while it's scheduling. And it can model and see, okay, if I place a job on the system, is that going to saturate any of the resources on the I/O path? But all of this assumes that we understand exactly what jobs are going to do once they're running on the system. So as the first step in our research, we assume we have an I/O oracle that's providing us perfect job I/O requirements, so the scheduler can be informed as to the decisions it's making. So now that we have an I/O-aware scheduler, we rerun that previous experiment, but we swap out the scheduler from I/O ignorant to I/O aware. And we do the same thing where we reduce the size of the parallel file system. So to start out, everything's fine, it's computing at 100%. We drop the parallel file system by 10%, and we see that applications still stay running 100% of the time. The way the scheduler is able to achieve this is it reserves some nodes. It delays the execution of some jobs that, if they were placed on the system, would cause contention. And so we see that the total number of nodes allocated at any one time is reduced. And this trend continues all the way through till the smallest parallel file system that we test. So an IO-aware scheduler does indeed ensure that jobs spend 100% of their time in computation, regardless of the capabilities of the parallel file system. Okay, so we've now moved from a scenario where the batch job scheduler just considered these compute nodes, and now it considers the entire suite of resources. But we assumed that the user or some other oracle was providing this additional metadata about what the IO requirements of the job is. So how do we get around that? So now we move to IO-aware scheduling with predictive methods. So initially we thought maybe we could rely on the user to provide this IO requirement. But historically, users are very bad at estimating how much time their applications are going to run on the system for. You can see that their accuracy is around 25%. And this isn't necessarily the fault of unknowledgeable users or users that aren't putting forth the effort. Users are incentivized by the system to overestimate, right? They want to give an upper bound on how long their application is going to run, because if they underestimate, now their application is going to get killed and they lose all their science. So that same incentive is going to exist for IO as well. So we can't necessarily rely on users to give us an accurate estimate. But what we can rely on is previous work in predictive tools like random forest or the tool Prion, which show that we can, with machine learning, get really good estimates for how long jobs are going to run and how much IO they're going to perform when they run on the system. And this is all done before the jobs actually execute. So just a quick primer on these predictive tools that I'm talking about. An example is Prion, which was developed by Mike, who's in the audience here. The way this works is it takes in user job scripts, consumes the whole script, so it's taking all of the information that it can from that script, runs it through a 2D convolutional neural net, and then that neural net's going to tell us how long it thinks the job's going to run for and how much IO the job will do. So this looks really bad without the animation. The IO oracle should be replaced with Prion, and then the predictions are being fed into the scheduler. So now the question becomes, how do we use these predictions in the scheduler? So as our simulation's running, whenever a new job is submitted, our scheduler stops and takes a snapshot of its current memory. So it stores what jobs are currently running and which jobs are currently in the queue. And then it queries Prion to get both Prion's predicted runtime and the predicted IO. And from this point, now our scheduler can estimate when jobs are going to start and when they're going to stop. So we can take the jobs from the queue and make those estimates. So now our scheduler has a rough idea, when are all of our jobs going to start, when are they all going to stop, and how much IO are they going to perform when they run. And we can use this to estimate what the overall system IO will be. So at any given time, we can look at what jobs are running, sum their IO, and plot that. But the thing that we're really concerned about is when IO activity is at its max, these IO bursts. That's where we want to concentrate on, and that's what we want to make sure that the scheduler can anticipate and account for. So in our evaluation, we consider an IO burst any time when the IO activity exceeds one standard deviation above the mean. So now that we have a way to predict or anticipate when these bursts will occur, how do we score how well our scheduler is anticipating these bursts? Well, given a real IO trace with real occurring bursts and our anticipated bursts, we score them by first marking out when the bursts actually occur and when they're anticipated to occur. And if there's any overlap, like in this case, we anticipate a burst, the scheduler anticipates a burst, and a burst actually occurs and there's overlap, so this is a true positive. In the case of this red anticipated burst, it does not overlap with an actually occurring burst, and so this is a false positive. And this burst that actually occurred does not overlap with an anticipated burst, so this is a false negative. And then we additionally have this idea of an anticipation window. So we add some time on either end of the burst, and if our anticipated burst overlaps with that window, we consider it a true positive. And this is a variable sized window that you'll see reflected in our results later on. So finally, now that we have our true positives, false positives, true negatives, false negatives, how do we turn that into a score or a metric? Well, we use the common precision and sensitivity metrics, where precision is the ratio of true positives over all positives, or the percentage of anticipated bursts that actually occur. And sensitivity is true positives over all actual bursts. And said another way, that's the percentage of occurring bursts that are actually anticipated. So given these metrics, we run a simulation on CAB, which has about 1,300 nodes, and we run 50,000 jobs from 2016 collected from Livermore's database. And we see that our scheduler is able to anticipate 70% of anticipated bursts occur, and our scheduler is able to anticipate 55% of bursts that actually occur. And that's with a window size of 5 minutes. And those metrics only go up as we increase that window size. So this shows us that using predictions from prion, feeding them into the scheduler, and having it anticipate bursts is a viable form of replacement in lieu of users providing these tags of I/O requirements. So we can strike this idea. Users no longer have to provide this, and instead we can integrate prion or other predictive tools. But what about the case where a user wants to submit an ensemble? They come to us with thousands or millions of jobs, and they dump that on our scheduler. How does our scheduler handle that? Well, this is where our fully hierarchical scheduler comes in. So first, let me go through some details on the existing state of the practice and state of the art, and carve out a space for where our model sits. So the most common scheduler model that we find is the centralized model, where we have a single scheduler managing all of the jobs and all of the resources. And because it's only a single scheduler, it has very low scalability. And we saw that in the very beginning of the talk, where the overheads were high and the failures were high. And because there's only a single scheduler and only a single scheduling policy, workload specialization is low. We're just applying one policy, uniform across the board. Doesn't matter what kind of workload you try and run. But because this scheduler has a global view of all the resources, it's very easy to institute multi-level constraints like our I/O or scheduling. Because it's the only one making decisions, it's very easy to ensure that those get satisfied. Moving towards more state-of-the-art, we see the decentralized model, which is a whole network of schedulers in like a fully connected mesh, and they're working cooperatively to make decisions on all the jobs and all of the resources. So because we have lots of schedulers involved in the decisions, we have high scalability. And because we have multiple schedulers involved, we could tailor each of these schedulers to different workloads and then get workload specialization. But because we have all these different things kind of working, they're all equal, nobody has the final say, it's really hard to ensure that these multi-level constraints are enforced, especially when you have conflicting schedules coming from all the different schedulers. And then the last state-of-the-art model is the limited hierarchical model. So in this scenario, we have a global scheduler, which has child schedulers underneath of it, and each child is responsible for a subset of the jobs and a subset of the resources. And much like with the decentralized model, we have multiple schedulers, so we get scalability, and we have multiple schedulers, so we get specialization, assuming these schedulers are customized for different workloads. But the problem here is that a lot of the times, with multi-level constraints, we have a global scheduler, so there is someone that makes the final call and can enforce these multi-level constraints. But the problem comes in implementation, where most of these multi-level or limited hierarchical schedulers have two different code bases running at the two different levels. So for example, at Livermore, they have Moab running at the global level and Slurm running at the local level. So now you have two different code bases and you have to have an interface between them. And things get lost in that translation. Like if Moab, your global scheduler, supports I/O, but your local schedulers don't, there's a conflict there. Now you can only enforce I/O at the global level, not the local level. And that also incurs a cost to scalability, because you have to translate and pay that cost of translation across the interface. So that brings in our solution, the fully hierarchical model, which consists of a hierarchy of schedulers of unlimited depth and unlimited breadth. So we have a plethora of schedulers that provide us with scalability. Each scheduler can be tuned to a specific workload, and users can actually create schedulers on the fly. So we have as much workload specialization as we want. And because there is a final scheduler that has the say, there's a global scheduler, and each of these schedulers is running the same code base and is seamlessly integrated, we can support multi-level constraints like our I/O or scheduling. There's no translation that occurs, and none of these resources get lost in translation across the layers. So how do we go about moving from this model to an actual implementation? So we added a Flux hierarchy module to the code base, and this consists of two pieces, the hierarchy launcher and the job distributor. So I'll now explain those. So for the hierarchy launcher, we're given an allocated set of resources for our ensemble. And this consists of 4 nodes. Each node has 16 cores. And we can launch a single Flux instance. So this is going to mimic the centralized scheduler, and we call this depth1. Or we can launch 2 levels of instances, with the second level having 1 instance per node. So this mimics the limited hierarchical model, and we call this depth2. And then there's the fully hierarchical model, which consists of 3 levels, where the final level, there's 1 scheduler per core. And in our evaluation, we refer to this as depth3. So this should note that these depth labels and this one-to-one mapping here between schedulers and resources is our focus for our evaluation. But our implementation can actually support mappings that aren't one-to-one. Okay, so that's the hierarchy launcher. So let's move on to the job distributor. So let's say, so in this case, we have a job source called the UQ pipeline, and that's a code base out of Lawrence Livermore National Lab that makes running these ensembles easy for domain scientists. So they come with their application code. They write an interface file that says, these are the input parameters, these are the ranges for those parameters. Please sample that space exhaustively, and then provide me with statistics on how these input parameters affect the output. So it's kind of like a full-fledged workflow manager. But the piece we're concerned about is the part where it submits those jobs to the scheduler. So we do some light modification to the pipeline to have it submit the jobs to Flux rather than a different scheduler. And then those jobs, go ahead and animation, the jobs flow into the root Flux instance and then get routed round robin across all of the instances at the upper levels. And then once they reach the lower levels, that's when the leaf schedulers actually schedule and launch these jobs. Okay, so I've described the 2 components we added to make this scheduler work. So now let me move on to some results. Here we have an evaluation of scheduler overhead on sleep 0 ensembles. So this is the same type of workload that I ran in the beginning of the talk, where there's no application runtime. So all of the time that you're seeing plotted here is just pure scheduler overhead. There's no actual application runtime. And in our depth1 hierarchy, which is just a single Flux instance, we tested between 1 and 1,000 or 2,000 jobs in the ensemble. We can compare that to our depth2, or what we're referring to as a proxy for the limited hierarchical scheduler. And you can see there's a transition point at around 128 jobs, where the cost of launching this larger hierarchy is outweighed by the benefit of the parallelism. And we see that same trend with the depth3, which is our fully hierarchical model, where once we get up to 16,000 jobs, the cost of launching that larger hierarchy is outweighed by the added parallelism. And as a point of comparison, we also ran this exact same test with Slurm, which is the state of the practice centralized scheduler used in a lot of the top 500 supercomputers. And you can see that despite Slurm being a production scheduler that's had years of all the bottlenecks being ironed out, and the Flux code base that we worked with being a production or a pre-production code, that we're still able to launch 11 times as many jobs in the same amount of time. So our fully hierarchical model really comes into play here and helps us scalably handle larger ensembles. But what about real-world applications? What about these applications that people want to run with the pipeline? So here's results straight from a real-world example at Livermore using the pipeline with our depth1. And when we see it compared to depth2, we see the same trend where there's some transition point at around 128 jobs. But where this is different is when we add the depth3 curve here. We see now that the depth2 and the depth3 are almost the same. And this is due to the fact that now we're dealing with applications that actually have a runtime. So if I plot the runtime of the job times the number of jobs, we would get the optimal make span. And you can see here how these curves have been shifted because of that optimal make span. And the other thing that we can note here is that it looks like these curves are starting to diverge. And if we could extend these lines out further, maybe we would see depth 2 go up and depth 3 stay flat. Due to a limitation in the pipeline, we weren't able to test with the pipeline to larger scales. But we were able to switch to using a proxy application that has the same runtime as the applications run by the pipeline, but don't require the creation of so many files on the parallel file system. And with this, we can test up to 1 million jobs in an ensemble, and we can see that the curves do in fact diverge, and that the depth 3 fully hierarchical scheduler is able to stay very close to optimal. So our model, the fully hierarchical model, is able to scalably handle even larger real-world ensembles. So in summary, next generation HPC systems will have a widening I/O gap and increasing importance of ensemble workloads. We've shown that I/O-aware scheduling can play an important role and ensure that applications spend 100% of their time in computation despite this widening gap, and that I/O knowledge provided by predictive tools are a viable alternative to user-provided I/O estimates. And then we show that hierarchical scheduling improves the job throughput and reduces ensemble make spans, and can schedule up to 11 times more jobs than the state-of-the-practice schedulers learn. And for future work, we want to consider the case where now, rather than a user showing up with 1,000 or 1 million homogeneous jobs in their ensemble, they come to us with a heterogeneous set of jobs. Some jobs are a little bit bigger in terms of number of nodes, some jobs run a little bit longer. We're not really sure. It's all just a big mix. How does our hierarchy handle in this scenario? Well, let me take you into a simple example here to illustrate one of the potential problems. We have a depth 3 hierarchy. If we zoom in on scheduler 2.2 all the way on the right, we see that it's in control of 6 nodes and has 2 jobs running, which are consuming 4 of those nodes. So 2 nodes are left idle. And this is too few nodes to run any of the jobs in the scheduler's queue. But if we zoom back out to the global view, we see that there's actually 6 nodes available across the entire cluster. So if only we could move these nodes from the other scheduler's domains into scheduler 2.2, it could run these jobs. And so this partitioning and fragmentation of resources across schedulers and the reduction of resource utilization is what we refer to as resource fragmentation. So to illustrate this problem, we simulate an execution of jobs on CAB, which is the same one we used for the one of the previous tests. We run 3,000 jobs, which cover a 26-hour period. And we show that, on average, the centralized model can utilize resources up to 73% of the time. So 73% of the resources are utilized on average, but in the fully hierarchical model, only 45% of the resources are utilized over time. So we see a reduction of 27%. So how can we solve this? So our proposed solution is, if we look here at our 3-level hierarchy, we want to have the child schedulers communicate both their surpluses and their needs to their parents, and then have the parents do a matching. So in this case, this child says that it has 5 idle nodes, and this child says that it could use an extra node. If it were to get that node, it could run another job. The parent does a matching between these 2 requests and says, okay, you send the node over to your sibling, and then forwards the remaining surplus to its parent. And now this root can do a match on these 2 requests and inform its grandchildren to exchange resources. And so now all of the schedulers have the resources that they need. And we've avoided the scenario where all of these leaf schedulers do an all-to-all communication. Instead, they're doing a scalable reduction up the tree. So this is all of the work that, all the publications that came out of this research. And this is the software that came out of the research, including modifications or additions of modules to Flux. And then here we have a timeline of the Flux code base, the changes that were made, where the forks happen, changes that were made, and how that was integrated back into the mainline Flux code base. And you can find all of the code used in the experiment shown on GitHub. Thank you.